First of all, I would like to thank the organizer to give me this opportunity, and so I'm going to talk about the Strichartz type estimates. I mean, generalized Strichartz. So the spherically averaged, I just took the name by Tao's paper. So Tao considered actually more precisely should be said like radius angular mixed norm estimates. So I just now this is the this is an outline. First, I will review. I will record some result on the Strichartz. I mean, it's very fundamental. Then the second part, I will talk about this is the main part, and the third part is application of this kind of estimate. Actually, also it is a motivation. It's from the Zihua systems. So consider the Schrödinger type equations. So here the d is square root of minus Laplacian. A bigger than 0. So this is a very typical dispersive equation, including Schrödinger equation and wave equations. So wave equation corresponding to a equal to 1, and the Schrödinger corresponding to a equal to 2. Now, the Strichartz estimate is the following. So this is the homogeneous estimate. This is the inhomogeneous estimate. And this norm, space-time norm, first take LR in X, then take LQ in T. This is a mixed norm, Lebesgue space. Okay? This is the well-known theorem of the Strichartz estimate. So basically, we have two results for Schrödinger and for wave. So for wave, the range is different from the Schrödinger. And of course, this is the natural scaling invariant conditions. Okay. So first, Strichartz. So in 1977, he considered the diagonal case Q equals to R for both wave and Schrödinger. For the mixed norm case, I mean, for wave studied by these authors, and for Schrödinger mainly by Yajima and Ginebra, the endpoint is due to Q tau in 1998. So now it's very clear that so the homogeneous estimate is sharp, but the inhomogeneous is not null yet. I mean, still open, the sharp range. But so in the radial case, even for the homogeneous estimate, we can have wider range. So here is the result in the radial case. Also for wave, for Schrödinger, the range is different, and they are almost sharp. So I will show you a picture. So this is 1 over Q, this is 1 over R. And the OABE, so is the Q's tau. I mean, this is the non-radial case. B is the endpoint. So this is the general estimate for the homogeneous case. And now for the radial case, you have this big range, except this endpoint. So in the radial case, at least for the homogeneous estimate, so everything is null except one endpoint. Okay, so this is the endpoint. Now the question is, can we have more estimates in the non-radial case? So as a generalization with the radial symmetry. So we want more estimates, but without the radial assumption. So that's, I mean, radial assumption is sometimes it's too strong, and many equations doesn't preserve the radial symmetry. So we need some generalizations in the non-radial case. So there are two kinds of generalizations. So if you would like to have more estimates, here we always consider time is globally. So t is globally in R. So if we want to have more estimates for QR, so naturally there are two approaches. Either you replace the left-hand side by a weak norm, or you replace the right-hand side by a stronger norm. Then you can expect more estimates. So the first one is, okay, consider the replace the right-hand side by a stronger norm. Here, the stronger norm, I mean, as a generalization of the radial case, we add the angular regularities. So radial function can be think as radially smooth because radial constant. So add angular regularity is very natural. So so for wave equation, it is studied by Sternberg and Rolansky. They obtain the estimates with the range exactly the same as the radial case, and with the almost sharp regularities. So S less than SW is false, and S equals to we recently with Chor and Lee, we proved that this estimate is true if Q. I mean, it's larger or equal to R. So partially on the endpoint line. So for Schrödinger case, so Chor Lee proved the same estimate for the Schrödinger equation with the same range as the radial case. But the optimal regularity is not known yet. So the second approach is to replace the left-hand side by a weak norm. Here the weak norm is, okay, replace this LPX by angular and radius variables, so separately. So here LS omega is the variable on the sphere, using the sphere. So this LP is the radius here. So if P equal to S, this is just LXP. So you simply is that you first do the integral in sphere variable, then do the radius variable. Because the sphere has finite volume, so LS they have strict inclusion. So if you take S is small, then this norm is weaker. But in the radial case, so LS is just a constant. So you take any LS, you just like LP. So in the radial case, this is just LQLP. So this can be also viewed as a generalization of the radial case. And this norm is weaker. So we expect more. So now that is the that is we call spherically averaged Strichartz estimate. So basically, you can think of, okay, you take L2 on the sphere. Why take L2? Because L2 is the most convenient one to work with, also the easiest one, because we have spherically harmonic expansions for the L2 function on the sphere. So now Strichartz type estimate for QP is bigger. The QP is always bigger or equal to 2. So this norm is strictly weaker than the LQLP. So then we expect wider range for QP. The mixed this space is often used also, I mean, in both harmonic analysis or in PDEs, so many times. So first one I know is, okay, in harmonic analysis, there's a famous problem for the multiplier for the Bohr. So this is the this T1 is the Fourier multiplier with simple characterization function of the unit Bohr. So in the radial case, Hertz proved the T1 is PP bounded in this range in the radial case, and it's very simple. Pfefferman has a famous result saying that T1 in the non-radial case, T1 is bounded in LP only if P equals to 2. So this is his famous result. And Cordova has a result saying that, okay, radial case, this range is the same as indicated by the Bochner-Riesz conjecture. So Bochner-Riesz conjecture for the multiple for the Bohr, there is a jump, right? But in the radial case, this is the range. Cordova showed that this operator is bounded in the same range, but replace the LP norm by this angular radius mixed norm. So we see this norm is kind of a replacement in the radial case. So in the radial case, so this is the indication. Okay, so if you expect if you have something very good in the radial case, so basically in principle you can say something in the non-radial case. So you have two approaches to say something. So this is the indication. So the second one is so for 2D Schrödinger equation and the 3D wave equation, so the endpoint is false. Endpoint Strichartz estimate is false. But so Tao proved this estimate and call this estimate is spherically averaged. The endpoint Strichartz. So we just take his name to spherically averaged. So Stefanov proved this estimate in the radial case, also proved it, but Tao proved it in the general version. And for 3D wave equations, the endpoint is also the 2 infinity, but they prove this estimate is true for any Q. So the endpoint 2 infinity is really just barely missing. So if you replace Q by any Q finite, it's true. And this is, the proof for this inequality is completely different from Tao's proof. Tao used the spherical harmonic expansion basically, but this one is completely different. Then Kato and Ozawa proved the endpoint for the Schrödinger, same result. So replace So it's just really just miss a little bit. Yeah.
Is there, do we need some cancellation for the operator wave equation? So it to the sine.
This one?
Sine of TD.
Oh, yeah. Maybe.
They use some cancellation property of for the consistent.
Oh, okay. I don't know that. Thank you. So not really these groups, but really the linear wave solutions.
But no.
I didn't check. Sorry. Yeah. But this is I'm sure. Yeah, for this one. Yeah, this one maybe I need to check. Yeah. Okay. So all this is a good indication, right? So replace the LR norm by some spherically averaged, you can expect more. Okay? And for the wave, let's already know. So for the wave equation, if you consider the mixed spherically averaged version, so they have this result. So for QP in the same range as the radial case, so this is generally the radial result without any loss. So the same range for wave. Okay. So now the question is, what about Schrödinger? So if I replace this by d square, can I have the same estimate as the radial range? Okay. There are some partial. There are some results. So the first one is in this paper. They proved some result for the Schrödinger, and not the whole radial range. In this paper, they deal with the wave equation, and the method relies heavily on the wave equation actually. So, in a journal work with Lee and Nakanishi 1, we consider this estimate. I mean, motivated by the Zihua system, the application of the Zihua system. We consider this estimate. In this paper we obtain a range better than wave and narrower than Schrödinger range. So in the radial case. So recently I improve to the whole range. I mean, at least for 3D and higher. So for 2D we miss the endpoint line, but for 3D in higher we have the same range for the Schrödinger equations, like the radial case. And this is based on the previous work, and I will tell you what is the key observation. So for the radial case, first talk about the proof. The radial case. The radial case is from I mean some results are known very early, but basically we just follow Shani South's idea. I mean, he proved the diagonal estimates, but without the endpoint. So he mainly consider the restriction estimate. So at that time, he didn't study the non-diagonal case. So, but when we read his paper, I mean, we just ask why not study the mixed case. So why just consider the diagonal case? So to study the non-diagonal case, we need two more estimates. So some maximal function estimates and some orthogonality to the endpoint. So the idea is quite simple. So of course, relies heavily on the radial symmetry. So you have a radial symmetry. So we use the Fourier Bessel formula to rewrite the solution. So rewrite the solution, linear solution, as a one-dimensional integral, oscillatory integral involving Bessel function. So this is quite a standard. I mean, these are quite standard. So here you have a Bessel function. This order is n minus 2 over 2. This is the order related to the Fourier Bessel formula. So we only need to care, we would like to have more estimates. So we only care that the x is very, very large. If it's very small, then it's trivial, because you use the L2, use the classical endpoint, you control everything. So only because x could be very large, then we need to really care. If x is very large, here you see s is essentially 1, so frequency essentially 1. So x is very, very large. So it is the asymptotic behavior of Bessel function that plays the role. So if x is very large, then we expect that essentially this has decay. So this has decay. So we really need use the decay information from Bessel functions. So by the oscillatory integral, we can write the Bessel functions as two parts. So if you simply using the decay estimate for wave, possibly it's okay, but for Schrödinger it's not okay, because if you only use the wave, you lose the oscillation here. You will not get the whole result. So the Bessel function decay also some oscillation, especially in our later result. So this area term you have better decay, but this main term will completely reduce to one-dimensional Schrödinger equation estimate. So for this one-dimensional, we can use the estimate for the one-dimensional Schrödinger equation. So second step is to do the space localized estimate. So you localize x to this dyadic piece, then you do the estimate. So Shao did only consider the r equals to 2, but here we consider r equals to infinity, because we need to cover the non-diagonal case. Okay. So in the endpoint case, we need some orthogonality argument to overcome the summation. Fortunately, here we do have. Okay. So in the general case, okay, this is a little bit more involved, but basically the idea is basically the same as the radial case. So our proof is completely different from their result on the wave. So their result on the wave used in a special way, like the property of the wave equation. So here we actually follow the ideas in our in the first work. So we need basically the idea is quite simple. So uniform Bessel functions with respect to the order, and the stationary phase estimate in a uniform way. So I will be more precise. So first, we use spherical harmonic expansion. So this is just like a toss paper. So using spherical harmonic expansion for the H, there you can write the free solutions like this. So there it will it is equivalent to show this estimate with a bound uniformly in nu. Here, nu only appears as an order of the Bessel functions. Nowhere else, so only here. If in the radial case, nu is just equal to n minus 1 over 2, so only 1. But now in this case, we have a family of the Bessel functions, and we want a uniform bound with respect to this nu, and it is equivalent. So this is the only way. I mean, we didn't have any loss. I mean, to ask too much, but this is what we want, equivalent. So now in the radial case, you have only one function, so you can use the stationary phase to decompose. So here, so at the first glance, you may think, Bessel function has decay like of the order r to the minus 1/2, but uniformly it decays worse. It's like the best one can hope is r to the minus 1/3, right, in a uniform way. So uniform decay. Now we have this decay. I mean, there are a lot of studies on the Bessel functions. So you have the pointwise decay, and you have the integral representations for this. So if we want to follow the radial case, we have 3 steps. First, here it's the same, that we need to consider r is very, very large. So which means we only need to consider the decay of the Bessel functions. So if we then in the radial case, we decompose the Bessel function into main term and error term. Error term has better decay, so it's fine. Main term, you plug in the main term, then you will you will use the one-dimensional Schrödinger equation result. So here we try to do the same thing. So here we need a main term and an error term, but in a uniform way, right? We should the main term. We should really check the dependence on the nu. We should really check. So you write it in the main term and the error term. There are 2. So we need 2 ways. So actually, if you look up some reference for Bessel function, in a uniform way, basically the principle is that. So if r, so this is simple. So uniform way. For example, if you have like this, it's very simple to exploit the information of Bessel function uniformly. If r is less, for example, in some way, if it's less, it's also simple by use this representation. Because if nu is very large, then if nu is bigger than r, then this phase is just has no critical point, because nu is bigger than r, right? So then then this case is relatively easier. The most difficult is it is called transitive region. Am I right? Yes. For Bessel function, is nu plus nu third maybe. I mean, in the study of the Bessel function, there is a like the transitive region for the Bessel function in this region, or in this region plus. Okay, so they actually already know that in this region, it is relatively difficult for the Bessel function. We have bad decay in this region, and here is the same case. So here is the transitive region. We really have problems, because for R is large, nu is small, then this phase we have critical point, right? So we need a second lemma. This is given in the Barcelo-Cordobas paper. So in this range, R is bigger than here. You can write the Bessel function into main term error term. But here now the error term decays like this. It's relatively bad, not as good as the radial case. So in order to deal with the 2D case, we need do more. So this is not enough in 2D. So we need actually a uniform expansions for the Bessel functions. Okay. Here the bound is uniformly, with respect to the nu. So in deal with the 2D, this is not enough for our purpose. So we need take out more maintenance. So here is the way. So we can deal with, for this H, we can further expand it, uniform way. So this is like so for the H we can reduce, we can expand K steps, so with a better decay. So so essentially we can expand the Bessel function in a uniform way. So in a very careful way. So this is useful in 2D, but is not needed in 3D and higher. So how do I do this? So the first, because I always try to reprove this lemma. In that thesis the thesis is not very clear. I didn't see clearly the proof. So then to reprove the lemma and find we can expand it in a uniform way. So consider the oscillator integral. Here we are concerned with the decay of I lambda. The I lambda decays as lambda goes to infinity. But the different point is we allow this phase function phi depends on lambda. So it is not a universal function. It depends on my decay parameter. So I lambda phi x, but phi x may depends on lambda. So by the Van der Kolk lemma gives the uniform decay, but I need to catch the oscillation. So there are many references for the oscillator integral, but I just I'm not happy with any of that, because I am really worried about checking the dependence of the parameter. So in Stein's book, he has an expansion, but I'm not I don't feel safe to use that in my case. So I redo it. So this is the normalized condition. So this is the normalized condition. So remember, my function phi may depend on lambda, but I first normalize the condition. Then by this condition, I can write this I lambda as this. Now the point is here R has a universal constant here C. I mean, of course, you after normalize, then you have a universal constant. So there, any time if I want to apply the oscillator integral and want to catch the oscillation, so I always normalize the condition first, then use this. Then I will not worry about the constant anymore. So this is the argument for this is very simple. Basically the same as Stein's book and Zosky's book. Zosky's book write in a very clear way. But this one is trivial. I think it's implicitly writing in the book, but not in their theorems. So in the theorems, I always worried about he didn't say anything about the dependence. But here, in order to apply this to the Bessel function, our function phi depends on lambda. So then I also have the expansion, you see, for the uniform way. So after normalized, you have a nice one. So by this, then I reprove the Cordoba's lemma and get a uniform expansion. So now do the uniform stationary phase estimates. So the key observation, I mean, is that so we in the previous work we simply decompose the Bessel function into three regions. So first, I mean, transitive region, I mean the simple range and the simple range. So this is in the previous work. In this range, so in this simple range, we use the integral representation formula. In this range, this is already quite easy. So you have if R is very close to nil, then we have a very small support to use. The difficulty is from the transitive region. So the transitive region before we didn't do any decompositions. So the key observation is that okay, in the transitive region we still do a final decompositions. Why do that? Because for this estimate we find the phase function depends on this. So after careful calculation, so we need to decompose the more in a final way for the Bessel function in the transitive region. So that's that, and we can catch more oscillatory effect. I mean, this is depends on the phase function do the decompositions. So this is also quite simple. Okay, and in 2D there are more difficulties. Not only the transitive, but also in the other range. In the other range, in 2D there is also more. But in 2D, if we use the expansion to this, then we can I mean in other range we can also cover, I mean, deal with some difficulties. So in 3D and higher, only this range cause problems. Okay. So okay, now talk about the Zarkarov system. I mean, this is actually is the motivation of the estimates. So Zhao system is the 3D Zhao system for the coupled equations. Schrödinger wave with two derivatives. Here is the difficulty. I mean for Fourier positives at least. So it has mass conservation and energy conservation. Also preserve the radial symmetry. So it is a rotational invariant. Formally, if you let alpha go to infinity, the Zhao system reduced to these cubic Schrödinger equations. So this is the limit equation. So essentially, we would like to cover all the results if for analog to the Schrödinger equations. So what I mean is, if Schrödinger equation has some result, we wanted to prove it for the Zhao system. And the first one is that not the first one. For the Fourier positives in 3D, Bogin and Colliander has a result showing that global Fourier positives for very small energy. Actually, his space originally is not exactly this. So, but his proof, their proof is based on the XLB method, essentially time local analysis. Okay. So previously, applied to this result, there are many works. Also, in particular, Professor Tsutsumi and Jenny-Blanc and Vella had a very classical result for the Zhao system in all dimensions, and prove the whole Fourier positives in the subcritical range. Okay, and there are many other works, so dealing with the low regularity problems. And on the limit, so you make the limit rigorously. So there are some work, and blow up. Then Frank Miller has a result in 3D. And the scattering theory consider the final data problems. So there is some work. Okay. Now the problems for the Zhao system, to me, the interesting problem to me for Zhao system is the following three problems. The first one is, okay, so Bogin-Colliander solution exists globally. What is the asymptotic behavior as t goes to infinity? So we expect a scattering, right, in 3D. The second one is the existence of finite time blow-up solutions with large energy or negative energy, whatever. Just find any blow-up solutions. So Frank Miller didn't prove. He only proved that the solution either blows up infinite time or finite times. So not a really finite time. So finite time is still open today. The third one is how to make the subsonic limit rigorously. So in a joint work with Nakanish, we first obtained that Bogin-Colliander's solution, if you assume symmetry, so it's a radial, then it scatters in the energy space. So radial symmetry. So after this, we really want to remove the radial assumption. That's the whole motivation. So, okay, I think I may skip this. So no. So, okay. From this, for this, I should say something more. Sorry. So for this, we use the normal form reduction. So normal form reduction and the Strichartz estimate. So normal form, usually Strichartz estimates, if you just use Strichartz analysis, you didn't use any bilinear or nonlinear structures, nonlinear interaction structures of the nonlinear term. So you only use Holder inequalities, right? But in the Zihua system, there are very good nonlinear structures, so nonlinear interactions. So normal form is one of them to catch the nonlinear structures. So normal form catch, normal form catch one. So basically, there are two structures of Zihua system. So the one, now we know better because we have many tools to exploit that. So the first one is the non-resonance structures. So this term is from, I take it from Tao's paper. So non-resonance or non-coherence. So there are two. So if you use the space-time resonance language, you will see the space resonance, time resonance. So actually the structure is the same. So there are already many standard tools to catch the nonlinear structures. So normal form is one of them, but catch only one. So catch the non-resonance structures. So Bulgarian space catch both. The space-time resonance method catch both. Catch you use the structure in a different way. So for this is essentially integration by part, and they make it clearly and generally, but prior to that, I think this was already used many times by Japanese groups, right? Especially, I think Nakanish and his collaborators have used this in many problems. But they call it a space-time resonance method. Before that, there is no name for that. So. Also, you see, we here we use normal form. We use one structure. Actually, there is another tool to use the other one, to use the non-coherent. I didn't write it here. The other one is the bilinear Strichartz estimate. So bilinear Strichartz estimate actually will use the non-coherent structures. So that's can one use the bilinear type Strichartz estimate to improve our result? That's our next project. So here we only use normal form plus Strichartz analysis. Normal form use one structure. Strichartz didn't use anything. But to handle the quadratic interactions, we need to assume radial symmetry. Here, radial symmetry is really important. And here, the estimator in the new triangle is also really important, because to handle the quadratic nonlinearities. But definitely, we know we missed something. There is another good structure that we didn't use. Non-coherent, right? So for the problems, we missed something, but we assuming radial symmetry. So this is kind of like compensation for that. Okay. So what about the non-radial case? What about the large energy data? This is the next objectives. So in the non-radial case, we rely on the spherically averaged Strichartz estimate. So that is the main motivation. So the first one is that, okay, here you have, so in the radial case, we have scattering result. In the non-radial case, if you add one order angular regularities, so still scatterings. So this is used this is just rely on the spherically averaged Strichartz estimates and the normal form. And then recently, so I used the new more wider range, so I can improve the angular regularity to this range. But the dream theorem would be s equal to 0. So this is one of my favorite problems so far. So I really want to remove the angular regularity, but I don't have a strong feeling whether I'm pursuing something that exists. So maybe this is not correct at all. So I don't have any strong reasons. Okay, there's one more thing. In order to deal with the fractional angular derivatives, there is a technically thing. So essentially we will use the fractional derivative on the sphere, okay, which is okay because there are already some literatures addressing that, but to make it consistent with the normal form, because we need to deal with the Fourier multiple with the spherically derivative. So eventually we use the integration on the SO3. Also, for this I will use I need to use the Sobolev algebra on the SO3. This is the result obtained by Thierry Coulomb and his collaborators. So but this is only technical issues. So to remove the angular regularity, we really need something new. I think one point is how to use the other good structure, how to use the non-coherent structures. Okay, thank you.